explain about the padder module now. Before we go into the padder module, initially let's look into a bit of theory about this SHA-3 algorithm. The SHA-3 algorithm specifies four particular variants of the algorithm: SHA-256, SHA-512, Shake-128, and Shake-256. The Shake algorithms are known as XOF for extendable output functions. Essentially, these can squeeze out multiple number of outputs as long as outputs are required further. Now, there are two parts of any state: the rate and capacity. Together, rate and capacity sum up to 1600 bits. Now, the rate values for all the four algorithms are specified here. The rates are calculated by using this. Capacity is 2 times D, and D represents this number here, the 256, 512, 128, and 256. So once we get this R value, we have to ensure that all inputs are multiples of this R. Suppose the inputs are not multiples of this R, that is, there is not enough inputs to be a multiple of R. Then that's where the spadder module comes into picture. So what its task is to put out 1 followed by zeros and then a 1 for the remaining number of bits to make the input a multiple of R. Now that we have seen this, let's get into the module. This module, the padder, has clock and reset as input, 64 bits as input, and there is an invalid signal from the controller which is high as long as the data at the input is valid. Then there is a start calc signal which is a pulse when every new instruction comes into this Keccak core. Then there is a take-in. This take-in is high as long as the inputs are still present and there are valid inputs still present. For example, when start calc goes high initially, valid inputs start coming here, but suppose there is a delay at the input side, take-in will continue to remain 1 until this is last signal comes in. As soon as this comes in, take-in goes 0. There is 64 bits of output which is fed into the CPO module. There is one more output called out ready, which is high as long as the output is valid. There is an output called ACK, which is sent to the input. Which is sent to the module, whichever module is giving the input, to say that it has successfully taken in the input. There is an output called counter 0, which to the CPO module, essentially to signify when to stop shifting in data to the CPO. And there is another output called take-in edge, which is just a delayed version of take-in. This delay was required for the F permutation module for timing problems, to handle timing issues. Now there is this reg, which is essentially the output. This has been assigned to the output later. There is a counter, a 5-bit counter. This counter is required because all the 4 algorithms which this core is capable of implementing have variable number of input lengths. So this counter is loaded depending on which algorithm has to be implemented. That is specified by this input called mode. There is a latch last register, which is just the latched version of isLast. Again, this was required to handle timing issues and provide a sequential delay. And then there is this register called pad. This was used to signify that further padding must be done and that the inputs are not sufficient. Now, let's go into this first always block here. Upon resetting, this counter goes to 0. And whenever there is a new instruction, when start calc is triggered, or the inputs are between R and 2R, say for example, with then the counter must be loaded in twice because there is a multiple of R now. So to handle that condition, this taken and counter equal to 0 has been put here. And of course, input should be valid. Counter is loaded with 17, 9, 21, and 17. How we obtain this? Let's look at that. So for SHA 256, R is 1088. And since inputs are coming in as a multiple of 64, as 64 bits, we divide 1088 by 64, thus getting 17, which means we need 17 chunks of data from the input. Similarly, the other three have also been calculated. And this is the counter decrement logic. When counter not equal to 0 and input is valid or pad, then counter goes on decrementing. Next, the second always block. Here upon resetting, pad out goes to 0 and ACK also goes to 0. Now first case, the input is valid and there are more inputs coming in. That is handled by this case, where input just goes to the pad out and ACK is 1 to signify that the input has successfully been taken in. Next, this is the last input. Even then, input goes to pad and acknowledge has been set high. Next, in this condition, when we look at this condition, there is this latch last, which is just the latched version of is last. We can see that here. Is last has been latched here. And counter not equal to 1, which means that the inputs have been exhausted, but the required number of bits for the algorithm have not yet been met. So then padding is done. Initially, 1 followed by 63 zeros, which is 2 power 63, is outputted to pad out. Here we do not have to acknowledge, since the input we do not have to acknowledge any input module because then there are no more bits from it. Next, we say counter not equal to 1 and 0, which essentially mean counter greater than 1. Pad out will be 0, which is all the middle zeros. And finally, the last padding output, which is 1, has been outputted here. And once all the inputs required bits for the algorithm have been given out, pad out goes to 0. Then there is this always block where upon resetting latch last and take in reg go to 0. And here we just delay is last and take in as take in reg. This is also again done because there are some timing issues which needed to be handled. And now the next always block. Here we are handling pad register. Upon resetting, it goes to 0. Pad becomes 1 when is last, that is the last input has arrived, but counter is still greater than 1, which means that sufficient inputs for the algorithm have not yet been met. Then pad is triggered high. And upon counter reaching 1, pad goes to 0, which means that the padder's job is done now. Here, out ready signal, which is given to the CPO, has been handled. Upon resetting, this goes to 0. Else, out ready will be 1 if either pad or invalid is there. And finally, when there is no padding required or input is available, then out ready will be 0. So this is not very intuitive, but we had to make counter 0 the condition when counter equal to 1 because we later on figured out that we were counting one extra cycle. This is given to the CPO module. And then finally out, which is just assigned as pad out for naming convention. Thank you. Now I will explain about the CPO, serial in parallel out module. This module precedes the F permutation module and follows the pattern module. It takes in 64 bits of data in. There is an input called hash in it, which serves as the reset for this module. There is a load enable signal. There is also a clock, and there is a counter 0 signal from the pattern module. This signals up to when the CPO must continue loading in data. There is an input called calc from the F permutation module, and we shall look at its use later. There is an output called isLoaded, and this is going to the F permutation to signal when the required number of bits for the particular algorithm is loaded in. There is an output reg which is 1344 bits called data out. 1344 bits is chosen because it is the maximum length of rate value required for any of the four algorithms. This is used for Shake 128, which needs 1344 bits. The other three algorithms require less than these bits. So this will ensure that all the four algorithms can be handled by this module. Now, when we go to the first always block, upon resetting, which is hash in it, data out register goes to 0. If there is a load enable, then the data out left shifts by 64 bits to accommodate for the new data of which is going into the LSB. Otherwise, this remains the same. When we go into the second always block, we look at a register called isLoadedTemp. This temporary register was made to provide for a sequential delay which this isLoaded signal required. Now, how we load this is upon resetting it goes to 0, and upon this counter 0 signal, isLoadedTemp goes to 1. This signals that the CPO has been loaded with all the data. Now, this calc signal is useful if the F permutation module is busy processing the data from a previous input. In that case, this isLoadedTemp will continue to remain 1 until the data which has been loaded into the CPO currently is also taken into the F permutation after it finishes the previous processing. Now, in the third always block, we look at isLoadedReg, which is just a delayed version of isLoadedTemp. This is going to the F permutation module, and upon receiving the signal, the F permutation will take in the input data.
Let's look at F permutation block. Mode is telling about the algorithm type. Clock is to clock inputs. Reset to reset all the registers. Input is taken in with length of max of R rate bits, which is 1344 bits per shake. It's a maximum. End ready says if the input is valid. Acknowledge is given back to the CPO register to acknowledge that we have taken in the input bits to be latched to perform the round. Output is of 1600 bits, which are sliced and taken into piezo register again, and out ready gives that the out is valid. Squeeze signal is taken in to tell that the outer module needs more bits, and this will perform another squeeze function through the same round again to give more bits. All the bits. P acknowledge is from the piezo register that the output was latched and was taken in. Last in is a signal which says if it is still taking an input based on is last, and uh, it's the CPO is loaded. So this last in is latched and has a delay of one clock cycle. To mitigate that, we have used first last signal, which is a pulse, uh, which comes just one clock cycle before. These two are used to latch another register called last in register, which basically tells if the input we have taken is the last input and it should stop absorbing after that. Calc out says if to calculate, if it is calculating inside the module, input of 1344 bits are here and 1600 bits are of output. Mode is of 2 bits. Squeeze signal, P acknowledge, last and first are given. If I is the round number, which is 1 hot encoded, and round in is of 1600 bits, and round is out also is of 1600 bits. Round in is sliced with the input based on the mode should be coming from. And round constant is given from the PROM based on the round variable, which is based on I again, and accept. Update says if to update the output register. Accept is to say if we are accepting input from the outer module, that is CPO. Accept is calculated using InReady and not of calculate, which is shown right here in the diagram. Input is, sorry, the round constants are based on the round number, which is first reset, and then it's left shifted and appended with accept or squeeze and calculate, not calculate. When it is accepting input for the absorption, or it's trying to squeeze to give more bits, and it stopped calculating from the absorb phase, which is given here in the logic. We have calculate, which is first reset because it shouldn't calculate at the start, and then the calculate logic is based on these three conditions and which are odd. Calculate becomes 1 if it was calculating before and the last round wasn't performed yet. That is set by this block, and which is given here in the block diagram. I of 22 says if it is the last round. If it is not the last round, calc is going to go high again. When it starts accepting to absorb, the calculate goes 1 again. When it's trying to squeeze and it's not calculating from the previous absorb, and it is not taking in any input to absorb, calc becomes 1 to give more bits. Update is given to update the out register, which is set using calculate or accept. When it is trying to calculate for squeeze or absorb, or it started accepting the inputs, the update becomes 1. And calc out is just calc which is given to the external modules to tell it's still calculating. Acknowledge is just accept. It is acknowledged back to the CPO saying it has accepted the signals. Sorry, the input. Out ready becomes 0 and it becomes at reset and it becomes 0 when it is accepting some input to absorb or the PISO has loaded in the output from the output register of F permutation to the parallel register. It becomes 1 when the round has completed and it's the last input we have been taking. If it is the last R bits, the absorb has ended and the I22 gives it's the last round. So the out ready becomes 1. Bit slicing is given here for the round input. This is for SHA 256 and this is for Pi 12 and this is for Shake 128 and this for 256. The R or rate for these functions are given by 1088, 576 and 1344 and 1088. For giving an input or absorbing, the first R bits are XORed with output and the remaining C bits are appended to the output, sorry, the input of the round. R plus C totally gives 1600 bits, which are given as round n. So shaft 256 takes 1088 of input and uses the other C bits to output from the output, and the out is also used to XOR with the input because SHA works like so, and this the input comes in of R bits and the other bits are from the output of the previous round. When the rounds have the 24 rounds haven't finished yet, the output is fed back into the round, or this can be used for squeezing also. Squeeze or round not done. 24 round not done yet. Last in register is the latch I have told you about. Last in gives if it's the last chunk of the R bits which we are taking in. First last is the same pulse which is telling if this is the last input. And these both are last in based on this OR condition. And the round input is given to this round function, and round constant from the PROM here is given to the RC, and round out is the output of 1600 bits here. Round variable is to select the round constant, which is given through this round variable, which is given to this PROM here. The accept signal is given here. The calculation logic is given here. The slicing of input is given here through this mux. And if to take in the input or take the output here of this else if block is this other mux. And this is the output register I was talking about. And this output is given directly out and the calculation is given out. This D flip-flop is for the last in register, which is based on the last in and first last. Thank you. Let's look at round function. Round function takes in 1600 bits and it outputs a 1600-bit output, and the round constant is given from the PROM. These are the intermediate stages given as wires, and it starts with juggling or permutation, which is initial permutation, IP stage, and then it is made into a 3D matrix of 64 cross 5 cross 5 bits. Each are called slices, and this is made into a beam 2D matrix, which is given to the theta stage. Theta stage performs this substitution, specific substitution, which is given here. And this intermediate C matrix is given back to the row function, which performs this operation and which can be seen here. Then this D matrix is given to the pi function, which computes the specific substitution, sorry, permutation, similar to a row function, like this. Then this is given to the chi stage, which is a substitution again, based on this criteria, which is given here. Then this progresses to the iota phase to be a Zord with the round constant for that specific round. And then the output is all again juggled or permuted, and it is outputted again. And this is the flow of the round function. First theta, then rho, and then pi, and then comes each chi, and then iota, and the input of round constant is taken, which can be seen here similarly. Thank you. Let's look at the piezoresistor. It's the register after the F permutation block, which would be taking in outputs and latching it into the register and shifting it serially to the FIFO. And the data input is taken as 1344 bits of R bits, and then the input is latched into the data register. Reset is to reset all the registers. Load enable is to load the input based on if the F permutation has performed out ready. And shift enable is to say to shift out the number of appropriate bits for the specific algorithm bits. And this is based on the algorithm. For shake 256, which is mode 0, would be shifting out 4 chunks of 64 bits, and 1 gives the modes 512 SHA, which shifts out 8 chunks of 64 bits, and mode 2 gives shake 128, which shifts out 21 cycles, and mode 3 shifts out 17 bits, 17 blocks of 64 bits. Clock is to clock all the inputs. Out ready says if the output is ready to be shifted into the FIFO, and this becomes the write enable for the FIFO. Data out is the 64-bit chunk which are going to the FIFO. P acknowledge gives it back to the F permutation block to acknowledge if the output was taken. And let's go through them. P acknowledge is same as load enable. If the input was loaded, it is directly acknowledged and given out to the F permutation block. And we have data which is reset on reset signal, and then the data is loaded in based on load enable, which the logic is given here with through this mux. And there's the shifting, which is an else if statement, which is preceded before the load enable. So there is another mux to shift left, and this is the number of bits it's shifting. It is 64 bits here. And we have out ready, which is given by load enable. If the output was loaded, then the next cycle, the piezo register says the output is available and can be shifted into the FIFO. When the shift enable is turned on, it is trying to shift out the outputs, and if the shift enable is not on, the piezo has been exhausted and all the inputs are out. So the out ready becomes 0. Data out is given the MSB bits of the data register. Thank you. Let's look at our synchronous FIFO. Buffer width is set to 5 now, which is 2 power 5 locations, which is 32 locations, as we'll be needing only 21 locations maximum, which is 1344 bits. 64 bits are used in each location, and there are 32 locations of them. So there are 32 cross 64 bits. Buffer out is used to read the buffer, input to write into the buffer. Read enable should be turned on to write it, and read enable should be turned on to read it. And buffer empty says if the buffer is empty, or full is given the buffer full, and output valid says if the buffer output was valid. FIFO counter says number of valid locations stored. Read pointer says pointer pointing to the read location, and write pointer gives the writing location. First, the read pointer and write pointer are initialized to 0. Whenever read happens, it is incremented. When the write happens, it is incremented. Whenever the write pointer is being incremented, it, it is filling the buffer in with these locations with buffin. Similarly, read pointer pops out the data value whenever it's being incremented, and it outputs to the buff out. And buff empty and buff full are assigned using this combinational statement. FIFA counter is 0 and equal to buff size. And when it is being read and written together, FIFA counter does not change and stays in the same state. But when it is being written to, the read pointer goes up and FIFA counter also goes up. When it is being read, it becomes negative, sorry, it becomes 1 lesser than the valid inputs before. Buffer empty, when the read enable is turned on and the buffer is not empty, we read the buffer memory at the read pointer location, which is outputted. And when it is not being read, the buffer out stays the same value. And the out valid out valid is turned on when it is being read read also. Out valid becomes 0 when it is not being read, and when it is being written into the buffer memory is written with the inputs, and when it is not, it writes the same value back into the buffer memory. Write pointers and read pointer are initialized with zeros, and when it is being written into, it just increments. When it is being read, the read pointer similarly increments. Otherwise, they stay the same state. Thank you.
So now I'll explain about the top module, the Keccak V1. This input contains clock and reset as an input, 64 bits of input, and also the mode as an input. This mode determines which algorithm should be performed. There is also is last, which is a pulse indicating the last input value. There is a start calc, which indicates a new instruction, which and is also a pulse obtained from the controller. There is an input signal give me. This is from the module following this Keccak core. Essentially, it's a handshake signal where the module following this, which is the sampling unit, says it needs more bits. There is an input known as invalid, which is high as long as the data at the input is valid. There is an output 64 bits out. There is an output ACK to the previous input module to say that it has successfully taken in the input. And there is an output out valid. Out and out valid are given to the sampling unit following the Keccak module. Now, each of these modules have been explained in videos. Here we'll discuss about some of the other signals that are defined in this module. Hash init is the reset to the CPO. Essentially, it's either reset or start calc. As soon as this happens, the CPO register will be reset. There is one more signal known as squeeze, which goes to the F permutation. Squeeze is triggered whenever the the sampling unit needs more bits, and but the buffer, the FIFO at the output is empty, and also not of shift enable. The shift enable is a signal from the piezo. This means that there is no more output at the piezo even, and absorb done. So all the inputs have been successfully absorbed and mode reg 1 because squeeze can only be done for XOR functions. XOR functions are shake 128 and shake 256. The other modes cannot squeeze. Now, in this always block, we'll define mode reg. Mode reg just takes in mode which is obtained from the instruction and then latches it at start calc. Then let's in this always block, there is a signal called taken. This taken is used to indicate the time duration for which absorb must be done. Essentially, it goes one at start calc and remains one until the last input has come to the module. Next, in this always block, there is this outread, which is actually a redundant signal, hasn't been used anywhere. Then let's come to this one. Here, there is a counter out. There is already one counter if you remember in the padder module. There is also one more counter and this is used for the piezo module. So piezo loads in data parallelly and shifts out serially. Depending on the algorithm, the output length can vary. So the number of cycles the piezo must shift the data out also varies. So we load this depending on mode reg. 4, which is essentially SHA 256. So this 4 is obtained by dividing 256 by 64. So it has to shift out 4 cycles of 64 bits data. This 8 is for SHA 512 and this is for Shake 128 and this is for Shake 256. But again, these can be loaded again for uh, extendable output if multiple squeezes are required. So this 21, after it goes to 0, if more bits are required from the sampling unit, it can again be loaded and 21 more cycles shifted. Then, in this always block, there is a signal called absorb done. Essentially, what this does is whenever F out ready is goes high after all the inputs are absorbed. Absorb can be multiple stages, which means that there can be multiple 24 rounds of F permutation. Once all of them have been completed, that is, the inputs have been exhausted, the final inputs are also absorbed, and this F out ready is driven high. This indicates that entire absorb process is done. This is again, we can see here is used in squeeze because we cannot squeeze until all the inputs have been absorbed. So then we come to this always block. Last in is defined here. Last in is used to say that the CPO has been loaded and not of taken, which means that the inputs have been exhausted and absorbing this round will be the last round of absorb essentially. So last in will be one and with this will be sent to F permutation. This signal was required for certain operations and timing issues in the F permutation. Then there is this out count 0, which is essentially again counterintuitive a bit because it is 1 whenever counter is 1 or 0. This is the output counter, the counter associated with the piezo. And finally, there is a shift enable signal. This shift enable signal is for the piezo. You can only shift out data from the piezo into the FIFO if the FIFO is not full and the out count 0 is also 0.
Hello, I am Amit Narayan Satpathy, and this is the test bench to test the Keccak code, which is implemented as a part of the hardware implementation of PQC, that is post quantum cryptography. This test bench helps to test the robustness of the implementation which has been developed by looking at the algorithm and reading through various research papers suggesting implementations of the same. Here we can see the block diagram of the overall system also given alongside the provided code of the test bench. The purpose of this test bench is to validate the design of the Keccak core, that is a cryptographic primitive critical to the implementation of secure PQC algorithms. The test bench ensures that each module in the Keccak core functions correctly, including input handling, padding, permutation, and output generation. It systematically verifies correctness by applying a set of stimuli and observing the outputs for the expected behavior. If we look at the architectural mapping of the test bench to the rest of the code, the Keccak core architecture includes the following main blocks. First, the input buffer accepts and temporarily stores incoming data. The second, the padder, which pads the input data according to Keccak specifications. Third, the F permutation block, which performs the core cryptographic transformation. and fourth, the output buffer, which stores the final hash results. Test bench interacts with these blocks via various signals like invalid, ACK, startcal, gimme, and outvalid. The test bench is structured into three main sections. The first section, initialization, resets the system and sets default values for all inputs. The second section, stimulus application, provides inputs to the Keccak core and monitors outputs. The third, output verification, compares outputs with expected results to validate functionality. Key signals here in the test bench include inputs, clock reset in mode is last start cal, gimme invalid, and outputs act out, out valid, and out buff empty. So we come to the first part, that is module declaration and initialization, which is in lines 1 to 34, as can be seen in the code here. So from lines 1 to 34. Here, module declaration happens, and so this block declares the test bench for the Keccak core. It defines all inputs, that is clock, reset, etc., and output signals, act out, etc., required to test the core. We also see instantiation of the Keccak core happening here. The UUT, or unit under test, connects to the test bench. Inputs like in, mode, and is last or is underscore last map to the input buffer and pattern in the code, while gimme and out valid interface with the output buffer. In line number 37 here, as seen in the provided code, at this line, we see clock generation happening, that is part 2. The clock signal toggles every half cycle defined by the cycle macro. This ensures synchronization across the Keccak core's operations. Next, we have part 3, that is the initialization block from lines 38 to 54. So from here, that is lines 38 to 54 is the initialization block. This block initializes the test bench. The reset signal is held high for 9 nanoseconds to reset all modules in the Keccak core. All input signals are set to their default states. Next, we have part 4, that is stimulus application, or the hint to start calculation, and this can be seen in the provided code from lines 55 to 62. So from here, that is line 55 to 62, we have stimulus application happening. This section simulates starting the Keccak computation. The start underscore calc signal initiates the process, and the in signal provides the first input word. The mode sets the operational parameters for the core. That is, the mode could be anything from 0 to 3, since we have a total of 4 modes being used in the core. Next, we have part 5, which is feeding data lines. And these lines are from line 73 to 80. So from here, that is line 73 to line 80, we have the part dedicated to feeding data. Here, multiple input words are sent to the core sequentially to simulate real-world scenarios. That is, real-world inputs, which would be given to the core as a part of the whole system. The loop increments the in value for a variety in the test data. Next, we have part 6, that is output verification from lines 89 to 97. So from here, that is line 89 to here, that is line 97, we have next up output verification. Here, the give me signal from the next module in the entire system, lying just outside the Keccak core, that is the sampling module. Um, this sends the give me signal, and this give me signal requests data from the output buffer. The test bench waits for the ACK signal to confirm readiness and checks the out signal for correctness. And then we also see that we have many additional cases, like we can see here after line 97, um, uh, all the way up to almost here, that is around line 150 and beyond, where we have additional cases where we absorb more data, toggle gimme, check buffer status, and also give more input in different modes. This is to have a robust and comprehensive testing of the test bench developed for this Keccak core and its implementation. Next, we have part 7, that is error handling, which lies in the lines 171 to 177, that is from here, line 171 to line 177 in the provided code. If any unexpected results occur, that is, in case of an error, the error task terminates the simulation and displays a message. This facilitates debugging by pinpointing the issues which arise. Next, we have part 8, that is waveform dumping from lines 179 to 185. So from here, line 179 to line 185, that's the end of the module. We have waveform dumping happening. Waveforms are recorded in the VCD file format for post-simulation analysis. And we see this step is crucial for visualizing signal transitions and debugging the test bench. Next, we can discuss the code mapping to the architectural blocks, which happens from this test bench. We see input handling in terms of the in, mode, and is last signals in this module, which are fed into the input buffer and padded. We also have padding, which is managed internally but controlled indirectly by the start calc and is last signals. We also saw permutation, which happens in the whole Keccak core system. It's triggered once sufficient data is absorbed. Also, we have output handling as the gimme and out valid signals interact with the output buffer. In terms of project integration, this test bench connects to the overall project by validating the Keccak code in isolation, providing confidence in its integration with other higher level PQC systems, even, and by supporting modular verification of cryptographic algorithms which have been built upon Keccak over the years. This code would also be usable for others because it takes a systematic approach which makes it reusable and adaptable. For example, parameters like cycle can be adjusted for different clock periods. Additional modes or data patterns can be easily integrated. Waveform dumps enable post simulation debugging and making the life easier for the users furthermore. Thank you.